Alright guys, we'll jump into part 2 here of our section 12.1 notes. And we get into partial sums of a sequence. So we talked about finding the nth term, all the terminology behind it, the first, the second, the third term, what a recursive formula would be for a sequence where we're writing the sequence in terms of terms that came before that one. And now we get into how to find the partial sum of a sequence. So let's recall a sub n, that meant the nth term of a sequence. And then something like a sub 3, this meant the third term of a sequence. All right, and based on this, we have some new terminology here. We're talking about sums, and sum just like you would think, adding things together. To figure out a sum of a sequence, at least terminology, we use a capital S. So we use this capital S, generally speaking, S sub n means the sum of the first n terms of a sequence. So instead of finding one term, we're going to find the sum of a group of terms, the first fill in the blank, however many terms you'd like to find the sum of. So a capital S sub 3, a sub 3 meant the third term. This means the sum of the first 3 terms of a sequence. And you can see the 3 there became the 3 there. We want the sum of the first 3 terms. And right now, we don't really know anything else. Eventually, when we get to sections 12.2 and 12.3, we'll get some interesting formulas for the sum of different sequences based on what category of sequence they fall into. So we'll talk about arithmetic sequences, we'll talk about geometric sequences. For now, however, at least in at this point in the chapter, the only way we really know how to do this is just by finding the first fill-in-the-blank terms and adding them up. And it's just going to be that simple for us. So we're going to find the first 4 partial sums of the sequence given by a sub n, the nth term equals 1 over 2 to the n. So our sequence is 1 over 2 to the n. They want the first 4 partial sums. So basically, they're looking for that information. And prior to getting any big, beautiful formulas for the way something was written, we're going to need to find the first 4 terms. Like I said, eventually, depending on what type of sequence it is, we might be able to go straight from this to that 4th partial sum without finding all of these. So right here at this part of the notes, I wouldn't ask you to find the 12th partial sum because I don't want you to find the first 12 terms. That takes a long time. How about 4 we can do? So we plug in 1 for n, we'll get 1/2 here. Plug in 2 for n, 1/4. Plug in 3 for n, 1/8. Plug in 4 for n, we'll get 1/16. We wouldn't really ever ask you for the first partial sum, but the first partial sum would always be the same as the first term itself. The second partial sum, this means the sum of the first 2 terms. So in that case, 1/2 plus 1/4, we get 3/4, common denominators. The third partial sum means the sum of the first 3 terms. In this case, 1/2 plus 1/4 plus 1/8, which is 7 over 8. In S sub 4, or the 4th partial sum, the sum of the first 4 terms, which is 1/2 plus 1/4 plus 1/8 plus 1/16, and that equals 15 over 16. And, you know, sometimes maybe some of your math brains kind of get into this kind of pattern where we look at the partial sums. And if you even compare the sum of the first term, the first 2, the first 3, the first 4, it's interesting. You might notice that the numerator is always 1 less than the denominator. Interesting patterns to think of. You also might notice that when that's the case, this number, these sums, are going to start increasing and getting closer and closer to some integer, but never actually touch that integer. That integer happens to be 1. 0.5, 0.75, 0.875. Not even going to take a shot at this one as a decimal off the top of my head, but it's getting closer and closer to 1, without actually touching 1. And this is going to get more important when we talk about infinite sums, which seems a little counterintuitive that we could actually add something up that goes off to infinity, but it's interesting. Things like this allow us to do that. Okay, and we talk about whether the sum would converge or diverge, and that's something that you can look forward to in a future section here in Chapter 12. All right, this is how you find the first 4, or a partial sum, the basics here, prior to getting any fancy formulas for some arithmetic or geometric sequences or any other sequences we'll talk about. Just find the first 4 terms, add them up. All right, and then we get into summation notation. Okay, just different notation to find a sum. This could also be known as sigma notation. Okay. The reason we have 2 different notations, or this one is used, is first of all, okay, it allows us to it does the same thing as the partial sum terminology, S sub n. So we can do that. But it also allows us to find a sum of terms beginning not with the first term. When we're using this terminology, S sub 3, S sub 4, that's always the first 3, the first 4, the first 6 terms, the first 8 terms. When we use this summation or sigma notation, it can allow us to find a sum of maybe a group of terms in the middle, like I want to find the sum of the 8th through the 14th terms, okay? And this notation allows us to at least express that that's what we're looking for, all right? So it's composed of a few things. It's composed of the Greek letter sigma. This is a sigma. Okay. And then you're going to see something like A equals a number. This tells us our beginning term for our partial sum. And then we're going to have a number up here. This is the ending term for our partial sum. And then this here is going to be the explicit formula for the sequence. It's not always going to be A, just like we talked about on a previous page. We can use really any variable. Okay? And then basically knowing the different parts to this notation will allow you to kind of put into words what we're asking you to do. So let's put that into words. Let's take a look at this first one. All right, this k equals 1 at the bottom means we're going to start with the first term, and we're going to go to the 5th term. So this is asking us, sigma notation, we want a sum. This is asking us, find the sum of the 1st through 5th terms of the sequence. In this, we're using a k sub n equals k squared. Find the sum, sigma means sum, of the, here's the beginning term, the first term, here's the ending term, the 5th term of this sequence here. Like I said before, the only way we really know how to do that is by finding the first 5 terms. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. We're just squaring the term. So 1, 4, 9, 16, and 25. I believe that would give us a sum of 55. We'll do B together, because this is finally one that allows us to do something in between. So this says find the sum of the of the 3rd through the 5th terms of the sequence j sub n equals 1 over j. So the third term, the fourth term, and the fifth term. Let's find them. 1 over 3, 1 over 4, 1 over 5. We need to add those up and get common denominator. I think we need to turn it into a denominator of 60. So that's 20 over 60, that's 15 over 60, that's 12 over 60, and we get 47 over 60 total. Fantastic. So at least now we know what they're asking us for. This would ask us from the 5th to the 10th term of this sequence. This is the first 6 terms of this sequence. Interesting, this doesn't have a variable. Might need to consider what's going to happen here, but you guys will do C and D. There's a little bit of an assignment here. And then lastly, rewrite the following sums using summation notation. So they want, or we want, to write this using our sigma notation. Looks like we're going to start with the first term since we have no dots here. So we'll use a equals 1. I don't know what the formula is, and I don't know which term this is. So we're going to need to figure out what term number this is, and then what is the sequence. So let's try to figure out what the sequence is, the explicit formula for the sequence. Well, this is the first term, the second term, the third, the fourth term. Those look like the squares, perfect squares, but they're kind of one higher than we need to. Okay, so they're one more than the term number. This one is actually 2 squared, 3 squared, 4 squared, and 5 squared, so we just add 1 to the n value and square it. My biggest recommendation when you're trying to come up with the explicit formula, after you're done, test it. Plug in a 1 here, a 2 here, a 3 here, and a 4 here, and figure out whether you get these terms. If you do, your formula has to be right. 256, that's interesting. 256 is which number squared? That would be 16 squared. Okay, but this is the 15th term. Alright, because we're adding 1 to the term number and then squaring it. So that would be the 15th term. So we're going to add the first through the 15th term of the sequence n plus 1 squared. That's how we would write that. Why don't you guys try B? We're going to start with our sigma. We'll obviously start with the first term. Here's the first term, the second, the third. We're not sure what term that is. That's going to be important. And we're not sure what the sequence is. So you're going to need to do some work to figure out both of those, and they'll go here and here. You'll know which term number you're dealing with here. Alright, cool. And that's the end of our section 12.1 notes.